Hello, everyone. It's March 16th. Whoops. There's an error in my agenda. Here we go. It's March 16th. Today, we want you to answer this question, please, in the chat for the attendance. You could travel back in time to anywhere at any time. Where would you go and when? When and where would you go? And also, please, I would like to hear some feedback about the midterm. I have not looked at it yet. But you can give me your feedback, please. Anyone?
I felt like the third question took a little longer than the other questions, but it was more difficult, but I think it was pretty fair overall.
Okay, thank you. Tristan? Anybody else? All right. No complaints? No praises? Either are fine.
I thought it was very comprehensive of what we've learned or what we're supposed to have learned.
All right.
I thought it was good.
Thank you.
Yeah, I thought it was just right, to be honest.
Goldilocks. Thank you. All right. Well, I like to hear bad feedback too, because that means I can make things better. So let me know if you think something should have been different. What about classes overall? Are we feeling the lack of spring break this year?
Yes.
Yes,
Absolutely.
Mm-hmm. Yeah.
it kind of really sucks.
Yeah. I'm sorry about that. I acknowledge that it sucks. I wish I could do something about it, but we have to trudge on. Because we have to, I am legally obligated to provide you a certain amount of teaching contact hours per semester. So, you know, I'm recording this, so you can always watch it later. So, can't make it to class and you need to take a personal day, let me know. Fine. And I'm sorry that spring break didn't happen. It'll just make us appreciate it so much more next year. Okay, do we have questions about the class? 3310, Physics 3310. Alrighty, we will hop back into the physics then. And let's remember, I'm sure you remember, but we're going to start back here just to start reviewing somewhere. Okay, so the Gaussian distribution was covered on the exam, so I know you know all this, but a Gaussian distribution function is something that is used to describe a system where you're measuring the same thing over and over and over that has tiny little random small errors happening. Okay, so when that happens, you should get a graph that looks something like this. This is a three-dimensional version. A two-dimensional version would be a slice of this along some axis. And the mathematical function that describes that curve is e to the minus x squared over 2 sigma squared, where sigma tells us how wide is that peak. Yeah. Okay. So we can use this idea of a Gaussian curve to kind of quantify the area under the curve compared to the standard deviation, the width of the curve, which we define by the standard deviation. So or 1 standard deviation across from the mean. If we go from the mean, 1 standard deviation this way, or 1 standard deviation that way, there's going to be 68% of the area under the curve in this. Sorry, everyone. My internet has been strange today. Okay. So I think I was talking about this Gaussian curve when things cut out. Does that seem right? Yeah, okay. So from, if we start at the middle, the mean is the middle, in this case 100. If we go to the right, 1 standard deviation, we have 68%. Sorry, 1 standard deviation to the right and 1 standard deviation to the left. Then that region, like inside that standard deviation, is shaded blue here. That's 68% of the area under the curve for any Gaussian. So we can quantify a relationship between standard deviation and area under the curve, or probability, if we relate that to a probability curve. So we can use a table to look up within multiples of a standard deviation the area under the curve, the percent area under the curve. And just as a reminder, we can use Chauvenet's criterion to reject a data point that seems suspect, that seems not quite right, seems out of place. The rest of the data points are pretty kind of all gathered together, and then there's one really weird one out here. So if we can't explain why it's, you know, not working, why it's so different from the others, we can use Chauvenet's criterion to basically prove that the probability of it occurring is like over here on my Gaussian curve. And that is really small probability that would happen. So it's really unlikely it's a real data point. So that's what we're doing with Chauvenet's criterion. So just as a reminder, you find the t value of the suspect data point, which is the suspect data point minus the mean. Take the absolute value divided by the standard deviation of your set of data points. Then you find the probability that your data point would lie outside the range t times the standard deviation. And you use the tables to do this. So you find the probability that it's inside, you subtract that from 1, and you get this probability that it's outside. You define this quantity n, which is the number of points times the probability that it's outside, and if n is less than 1/2, you can reject the data point. So we've already done an example of this, but it's been a couple weeks. So we're going to go into breakout rooms and do another example of Chauvenet's criterion. Here it is. I'm going to try to leave it up on my screen while we go into breakout rooms. And we'll also put it in the chat. I'm going to share my screen again in a second. Okay. There we go. Okay, and I did update the breakout rooms a little bit. I will show you that list here. We did have some people drop the class, and we had some very unevenly numbered, different numbers of people in breakout rooms. So we have changed it a little bit to be what's shown here, which I will also put in the chat. And then I'll open up the breakout rooms. Okay. All right. It should be open, and I'll put you in if you can't get it. Can we throw out the data point 5 based on Chauvenet and his criterion?
Yes, you can.
Thank you, Sean. I agree. And I calculated 0.42 for my little n value. Is that what, did y'all get something close?
I got 0.34. I
Oh.
don't know how.
Okay. Well, let's go through that. Okay, so remember the T suspect value is the first step. So, sorry, let me get this thing out of the way here. Okay, so for the T suspect value, we have the suspect, go back to the slide, the suspect quantity, so that would be 5. And we're going to subtract the mean. I got 10.8 for the mean, roughly. Y'all get 10.8? Okay. And then the denominator there is the standard deviation. So I cheated and did that on Excel. Here's the that problem back there. Here's the list of numbers. I'm pretty sure it matches the one that's given. And this is the standard deviation here. So I used STD, EVS, DEVS for sample. Okay, and then the mean is over here. Average is what I used for the Excel thing. Okay, so what'd you get for T? Or what'd you get for the standard deviation, I guess? Did you get 2.7 people? Roughly? Am I frozen? Oh my gosh. Sorry. I don't know. My internet sucks today. What'd y'all get for T?
.17.
Me too. Yes. Okay. Hopefully y'all all got that. Okay, so then we go to the tables. We go to the Gaussian table. Here it is. We will go ahead and zoom in on that. So this got cut off at 2.1, but we know the next row is 2.1, right? Because it goes up by 0.1. And then we go over to, we were trying to find T equals 2.17. So this is 2.11, 2.12, 2.13. Here's 2.17. That's 97. So the probability that it's inside T is 2.17 times sigma is 97%. So that means if this is 97%, 1 minus 97% is 3%. Okay. And then we take 3% times big N, which was 14. And that is 0.42. Okay. Anybody else get 0.42? Did you have time to finish? No. Okay. Got it. That's why you don't have an answer. Okay. Well, I will post a solution for this in case you need to see that. Try to give you a little more time next time. All right, let's talk about some new material. Come on, come on. Okay, weighted averages. Not a big deal. Weighted averages, not a big deal at all. Weighted averages are a thing we need to deal with when our uncertainty is not constant. If we're measuring the same thing over and over, and at some point the uncertainty changes, and then like changes again while we're measuring the thing over and over again, then a regular old mean doesn't seem like it would do as good of a job of describing the real mean. So now we can do a weighted average instead of a old-timey average. And I'm interchanging the word average and mean here because people do that all the time. So I'm just gonna do that too, to kind of get you into the practice of seeing that. So how do we calculate a weighted mean or a weighted average? Let's say we measure some values y sub a with corresponding standard deviation or uncertainty sigma sub a, and then y sub b with sigma sub b as its uncertainty, and y sub c and sigma sub c as its uncertainty, and so on and so forth. And notice that the uncertainties are different every time here, or we would just be writing sigma if it was the same. So if that's the case, then we use this formula that I am circling here to find the weighted average of our y value that we're measuring over and over and over. So we take this quantity, w, which is shown here. W sub I is 1 over sigma sub I squared. Okay, so we multiply that 1 over sigma sub I squared times y sub I, and we add all those up and put that in the numerator and divide by the sum of all the w sub i's. So w is a w because it's a weight, W-E-I-G-H-T, weight. The y sub i's with smaller uncertainty are going to get more weight, which is good because they have a smaller uncertainty. And the y's with a bigger uncertainty are going to get a smaller weight. They're going to matter less in the overall average. So that's good too. Okay, so the corresponding new uncertainty of the weighted average is going to be 1 over the square root of the sums of the weights. So it's all of the standard deviation, all of the uncertainties, but calculated in kind of an inverse because we inverted them in the first place to get W. Okay, so example on the next slide. What if we have 4 students? Each student is going to measure this acceleration due to gravity in Boone, and they get these results. 10 plus or minus 1 meters per second squared, 9.8 plus or minus 0.2 meters per second squared, 9.79 plus or minus 0.05 meters per second squared, and 9.979 plus or minus 0.02 meters per second squared. What is our best estimate for the acceleration due to gravity? A regular old average doesn't seem quite right because that 10 plus or minus 1 is a really crappy measurement. And the 9.79 plus or minus 0.02, someone took a lot more care to take that measurement. So that really is more, we should give that more weight. So that's what we do with the weighted average. Okay, so I again cheated and used Excel here. And I am narrating on the right what is happening in the spreadsheet on the left here. And then I rewrote the equations here that we're supposed to calculate. So this is just the data. 10 plus or minus 1, 9.8 plus or minus 0.2. 9.79 plus or minus 0.05, 9.79 plus or minus 0.02. So the weights are what I calculate in this column. And I did that by finding this right here. This is the weights. So each of these here is sigma sub I. So I took sigma sub I and squared it, and took the reciprocal of that, the inverse of that, and put that in this column here. And then the fourth column is going to be each value multiplied by its weight. So it's W sub I times Y sub I in this column. Okay, and at the bottom here, I'm adding up all the weights. This is the sum of all the weights, so it's all these added up is here. And then Then I'm adding up all of the weights times the values here, and that's this sum here. I'm sorry, that keeps changing. Okay, so the final G value here is going to be the sum of all of the weights times the values, which is this here. And I'm going to divide by the sum of all the weights, which is this here. So this divided by this is this 9.790157. So that's my weighted average. And yeah, it's close to 9.79 because my two best values with the best precision were 9.79, and those were the weighted values. Okay, and then my final uncertainty in that weighted average, that weighted mean, is going to be 1 over the square root of the sum of the weights. So I take this quantity, I take the square root of it, and I take the inverse of that, and I get this new 0.018487 quantity here for my uncertainty in G. So my final reported weighted mean and its corresponding uncertainty are going to be 9.79 plus or minus 0.02 meters per second squared. So I take this digit and I round up, and that's my digit, my one significant figure in my uncertainty, and that defines the uncertainty range or the precision of my G value. Okay, so that's a weighted average, that's a weighted mean. You do that when you have different uncertainties for your different Y values or different measurements, when you're measuring the same thing over and over and over and over with small random errors. Okay, questions? Okay. I encourage you all to cheat and use Excel or calculator or something from now on to calculate standard deviation, like the traditional standard deviation. It's a lot faster. All right. So if we don't have questions, we're going to do another breakout room. Problem 7.4 from your book. 4 measurements are made of the wavelength of a light from an atom. 503 plus or minus 10, 491 plus or minus 8, 525 plus or minus 20, 570 plus or minus 40. First, find the weighted average and its uncertainty. Is it worth including the last measurement or not? It's part 2 of this question. All right, so I'm going to open breakout rooms back up. And just go back to where you were, or Sam, go to, let's see. Yeah, here we go. Okay. You're going to have to re-choose your room. And don't go to
I'll go into whichever one has the least.
Okay, thanks, Sam. Oh, okay, now they're open. Sorry, y'all.
I was the host. I got them into their breakout rooms, Dr. Hester,
Oh.
except for Sean and Veronica.
Okay, yeah, thank you. Veronica, I'm putting you in now. Okay, sorry I had to rip you out of your breakout rooms, but class is almost over. So, oh my gosh, did it just happen again? I'm going to scream. Okay. Did anybody get a weighted average? Anybody get a final weighted average? Okay, Allison, yes, what'd you get? Or somebody?
I didn't write it down, but I think Sam did.
We got 499.
Me too! Woo!
Hey, plus or minus 6 was our.
Yeah,
New-
5.89, something, something, yeah, was the
Yeah,
uncertain.
that's exactly that's what we had. Yeah.
Okay, yay! And my internet did not die in the last minute, thank goodness. So I'll put a solution up for those of you who didn't get to see the steps. But yeah, what were somebody saying there? Okay, maybe I didn't interrupt someone. All right, well, next time we're going to talk about curve fitting. Woohoo! Finally, it's so important. So be thinking about this question. What is the goal of curve fitting? That's what I'm going to ask you next time, first thing that we do. So I will miss you so much, but I will see you on Thursday. Bye, everybody.
Have a good few days.
You too. Thanks.
Bye.
Bye.